So for the rest of the quarter, we're going to be or the rest of the, excuse me, the couple of weeks that we have class, um, we're going to be looking a lot at the p-value. So the definition of a p-value is the probability or chance of finding a result at least as extreme surprising. So it has to be as at least as extreme or surprising in settings identical to those in the actual study if outcomes happen by random chance alone. Okay. Now, the p-value can be thought of as a measure of reasonableness of the assumption of random picking. In other words, the null hypothesis. The smaller the p-value, the greater your doubt of the initial assumption, and the less reasonable the random chance explanation or the null hypothesis for the observed data. So if we have a very small p-value, less than 0.01, we have very strong evidence. Between 0.0, a little more than 0.01, but less than 0.05 strong evidence, down to moderate evidence for less than between 0.05 and 0.1. And then if we get above 10% or above 0.1, we have not much evidence. So we're going to use this chart for right now. If you have done looking at significance alpha, we're going to be doing that later. If that means nothing to you, don't worry. So based on the p-value, is random chance or just guessing a plausible explanation? Reasonable, believable for why Sarah got 7 out of 8 answers correct? No. Now, I typed this in so that you can pause it, write it down, and then come back. No, we have a p-value of 0.037. So we have, based on this, 0.037 is in here. So we have strong evidence against the null, in other words, against the she's guessing or randomly choosing hypothesis. Now, if she was just randomly choosing, she would get 7 or more correct only 3.7% of the time. And that's not very often, okay? So based on our findings so far, state our conclusion in the context. And at the end, in the next note set or two, we'll come up with I don't want to say a template, but effectively a template, how to write a conclusion. But we want to say what kind of evidence we have. In this case, we have strong evidence. And I give the p-value of what? That she is doing better than randomly choosing. Okay, so we have strong evidence of that because and you're like, well, wait a minute, whoa. Remember, we're looking to see how unusual it would be to get 7 or more, just if you're flipping this time a coin 8 times. We did it 1,000 times. Okay, we did that flipping a coin 8 times and see how many heads we got. We did that 1,000 times, and it happened less than 4% of the time that it was 7 or 8. So as extreme or more extreme. So more extreme being, or more extreme being 8, or as extreme being the 7. Correct. Now, while this is nice, is we're always going to get a different value, but we can use exact mathematical analysis. And we can find the exact p-value using the binomial. So if you're wondering why we did binomial, beyond the fact to torture you, there's actually a reason. So we're going to let x represent a random variable which counts the number of correct answers in 8 attempts. Now remember, we have Sarah getting 7 correct. Can this be binomial? Well, is it discrete? Yes, we can count the number. It's countably finite. It's between 0, including 0, up to 8. And also, we have only 2 options. She either gets it right or wrong. So what's the probability distribution? It's done by the binomial with 8 repetitions and probability of 0.5. Or you could write it longer. N equals 8, P equals 0.5. If you're wondering where the 0.5 came from, remember it's 50-50 because we're flipping a coin. Now, use the binomial probability calculation to find the probability that Sarah gets at least 7 answers right of the 8, just by guessing. This will be the exact binomial p-value. So this is great. Whoever calculates this will get the exact p-value that I will get here. So let's see, we know we want as extreme or more extreme. So 7 or 8 heads or getting them correct, we can add 7 and 8 together. Remember, they have no overlap, so we can just add them together. Then we're going to do 8 choose 7. Remember, she gets 7 right and thinking 1 wrong. And then she gets all of them right. And you're like, well, wouldn't it just be 0.5 to the 8? Yes, it would be. But I just want to show everyone that you can just use the formula. Now you may be like, well, why don't you just put 0.5 to the 8? It's the same number, because it won't always be the same number. Okay, that's only if it's 50-50, but if it's like 1/3, 2/3, like we did earlier in the quarter, not finding a p-value, but calculating this, you'd have to have 1/3 in one and 2/3 in the other. So if you do this calculation out, which you should practice, you get 0.03125 plus 0.00391, giving us a p-value of 0.0352, which is very close to the 1,000 repetitions when we did the computer simulation. Was the approximate p-value from our simulation of 1,000 repetitions close to this exact p-value? This is letter L. Yep, it certainly was. Is this p-value small enough to cast doubt on the assumption that for each question, Sarah is randomly choosing between 2 photos? And yes, and it's the same explanation that we used above. So that wraps up that example. We're going to do a lot more examples with this, so don't panic if it's not clicking the first time through. We'll be talking a lot more about p-value as we continue along.